Welcome back, students. In the previous lectures we have seen how to solve different problems using greedy method. The various examples that we have checked is a knapsack problem, a job sequencing problem, and a Huffman code. In today's lecture we'll look at a different problem which is named as optimal storage on tapes. How do I solve this particular problem? Using greedy method. Let's first make the problem statement. What's the problem statement in this case? We have n number of programs that I want to store on tape, a single or multiple tapes. N number of programs are to be stored on a tape. My job here is that how do I store these programs in a way such that when I retrieve these programs back, the retrieval time is minimum possible. We have to reduce the retrieval time in this case. So that's the problem statement. Now, every such program in this case has an associated length. Let's call it Li. Every such program has an associated length in this case. And let me take a typical example. If you're a 90s kid, you might be aware or you might have known something called an audio cassette we used to have. Now, this audio cassette, unlike today's CDs or the DVDs that you use, which have random access. So if this audio cassette, if this is my audio cassette or a tape or a magnetic tape, and I have to store my programs on this magnetic tape, and every such program has a certain length. So this is my program 1 that's stored on this much portion of the tape. Let's consider the songs. This song number 1, this is favorite song 1. This is your song number 2. It takes this much space on the tape. This is my song number 3. It takes this much space. Now those days, in case of these audio cassettes, unlike these CDs or DVDs, if you want to listen to the song number 4, you have random access. You can directly put the tape head on that particular sector where you want to listen to this. So assuming that the tape head is in the beginning, and if you have to listen to the song number 3, then you necessarily had to go through song number 1 first and song number 2. Then only it was possible for you to listen to song number 3. So essentially, to retrieve the program number 3, you have to first traverse through program number 1 and program number 2 to reach to that point, and from that point start the retrieval till you finish that. This is how things were stored on tapes. So it may be a single tape or it may be multiple tapes, and we can use sequential access in case of multiple tapes as well. This is the problem. Now my job here is that how do I reduce or how do I minimize this retrieval time such that the programs, any program that I access, there are various possible. Say if I put program number 1 here and program number 2 here, does that make any change? Does it make any difference? Or if I put my program number 3 in front of all these programs, and then I have to retrieve program number 1, which is here, again I have to traverse all these. So there are multiple permutations and combinations of these programs and lengths that are possible over there. Greedy method suggests that let's put the program with the least length, with the smallest possible length. Let's put that in the first sector, in the very beginning, and let's put all the programs in ascending order, in a sorted manner, in ascending order of their lengths or sizes. So this is the problem statement what we have. How to solve this using greedy method? With the assumption, this assumption number 1, that tape is positioned, the head which is reading the tape is positioned initially at front. This is the first assumption. And the programs, so this is my tape, and these are my programs I1, I2, I3, and so on. And 2-part programs are stored in order I I1, I2 and so on. Now if this is a scenario and I need to access or retrieve a single program, say an I3 or an I4 or I5, or let's in general say some ijth program. If I need to retrieve this particular program, how much time, how much resources does it require me to access this particular program will be some T of j time. The time will be T of j to retrieve I of j. It's very simple. If I have to retrieve I of 1, I say that I require time, some time. I'm not figuring it out how much time is that, but some time T of 1 to access I1. Likewise, to access I2 program, some time T of 2. Likewise, for some I of j program, I may need time T of j. Now, what is the T of j equivalent to? How do I compute my T of j? My T of j is sum of all these times, because to reach I of j, I need to go through these I1 and I2 and I3 and all these I values less than ij. So sum of all the times that I will be required to traverse from initial position to this particular position. So sum of all of lengths of the program. So let's say the length of 2 minutes, length of 3 minutes, length of 1 minute, length of 4 minutes. So sum of all these lengths will be the time to retrieve this program I of j. That's the value of T of j. So summation of L of I of k, where k varies essentially from 1 to j. So this I of 1, I of 2, I of 3 up to I of 4, 5, 6 up to I of j. So that's what I'm running the loop from. K of 1, that's from this position index 1, this index 2, this index 3, this is index 4, this is index j. So I'm running the loop from 1 to j, summation of all these lengths, all these times. So if this takes 2 minutes, if this takes 3 minutes, if this takes 4 minutes, then the jth program will be requiring 2 plus 3 plus 1 plus up to that particular program. So that's my equation number 1. That's time required to access some particular program ij is my T of j, and T of j can be computed using this formula. Now let's assume that all these programs, say beta I1, beta I2, beta I3, that they are all retrieved equally often. Let's put it here. All programs are retrieved equally often. So if I listen to the song number 3 twice a day, I might be listening to song number 4 twice a day. If I listen to song number 5 once a day, I might be listening to song number 1 thrice a day, making it almost equally often. So that mean retrieval time for every such time. So mean retrieval time is the average of all of these, will be 1 of n, summation of all these times. So T of 1, T of 2, T of 3 for all these times, where j varies essentially from all, it traverses between all, it varies between all the programs. So if I have 5 programs, so I'll be running the value from 1 to 5, that means 5 such programs, and T of I, T of j here will be representing the retrieval time for each such program, and this 1 by n time, how many number of times, the total summation of the total times divided by the number of programs will be my mean retrieval time. Now if I have to take it for all those lengths of the program, a single program has this much length, a retrieval of a single program takes this much time, retrieval of all the programs, mean retrieval of all the programs takes this much time. So if I have to find the minimized MRT value, that will be all the programs that are there available. So 5 programs if it was in earlier case example, and every single program, the time it takes for every single program. k varies from 1 to j. Now this is interesting over here. Let's try to understand what do I mean by this equation 3. Now this is my equation 2. This is my equation 3. Let's try to understand what I mean by this. So the minimum possible time that I minimized MRT will be here. This is the time required to access an individual single program. So this particular part here is essentially this equation. This is the time required to access one single program, and the total amount of time that will be required to access all such programs. So if I have, this is my tape, this is my program number 4. This particular thing here, this equation represents the amount of time required to access this program. That means if this takes 2 minutes, if this takes 1 minute, if this takes 5 minutes, the amount of time required to access this is 5 plus 1 plus 2. That's up to reach to this point. Then the amount of time that is required there, that's plus 4. That's program number J4. But if I see at the same time there's a single program, that's this part. But if I see that I also have to retrieve program number 1, I would also retrieve program number 2 or 3. So for program number 1, it's just 5. For program number 3, it's a 5 plus 1 plus 2. Right? So that's the summation part of this outer loop, the job of this loop. All these 1, 2, 3, 4, 5, all of these will be represented by the outer loop. Every single program will be represented by the inner loop. That's here. Let's take an example and try to solve this problem using greedy method. Let's suppose the number of programs here is 3. And every single program, remember, has some length associated with it. That's L1, L2 and L3 represent the lengths of the 3 different programs respectively. In this case, my L1 is 5, my L2 is 10, and my L3 is 3. Now, what is the possible ordering of this? The possible ordering in this case is always n factorial. That's 3 factorial. That is, there are 6 different ways in which I can write these programs, right? So in this case, it's a 3 factorial, which is a 6. Now, let's try to see all these possible combinations or orderings. Let's put this as I, ordering of I, and let's see the time required for this I. Now, I may put it like this. First, I store program number 1, that's with length 5, like this. This is my tape. I may put it like this. First on the tape, I put program number 1, and then program number 2, then program number 3. This is one possible way of storing my programs on this. So the ordering can be 1, 2, and 3. Let's see the amount of time that it requires to retrieve all these programs. To retrieve my program number 1, the tape is initially located here. To completely retrieve, the program starts here and finishes here. To completely retrieve my program number 1, I need to traverse from this place to this place, which takes me 5 units of time. And to retrieve my program number 2 here, I need to first reach to this place, then complete the required tape, which is the length of that particular program. So that will be my 5 plus 10. So remember, to retrieve this program, and assuming that the head is basically located at the initial front, we have to first traverse from initial front to the starting of the program, then complete the length of the program. That sums makes it to 5 plus 10. And likewise, to retrieve my program number 3, I first need to traverse to this place, and then from there I can start retrieval of this. So I can, for program number 10, it can be 5 plus 10 plus 3. Let me reiterate it again. If I store these programs, these L1, L2 and L3 lengths, which are 5, 10 and 3 correspond respectively, if I store them in the order of 1, 2 and 3, that's program number 1 in the beginning, followed by program number 2, followed by program number 3, then to access my program number 1, assuming that the head is basically placed in the initial position in the front, I will start from the front, and it will take me 5 units of time to complete the retrieval of program number 1. That's where how this 5 is basically the reason for the 5 in this case. To access program number 2, I first need to reach to that location from the starting location. So from the beginning location I need to traverse this 5, then I reach the beginning location, then it takes me 10 more units of time to complete the retrieval of program number 2. So that's how it gets to 5 plus 10, and likewise for the third. Let's take another permutation. The another permutation here can be, I store the first program in the beginning, then I store the third program, then I store the second program. It's like this. I store the first program in the beginning, then I store the last program. Let's see if it makes any difference. So in this case, to retrieve program number 1, I'll be needing 5 units of time. To retrieve program number 2 in this case, now that I have to reach to this place, that takes me 5 units of time. And the retrieval completes itself in 3 minutes, so that's 5 plus 3, which is obviously lesser than the first one. And in case of program number 3, so I have to take it 5 plus 3 and then the amount of time required. Let's see, this is here is equivalent to 38, the first part. There's some difference, there's some optimization if I change the order. If I make the change in the order, the total retrieval time basically reduced from 38 to 37, 38 to 31, sorry, with the difference of 7 units of time. Let's take another possible combination in this case. Another possible combination can be that I take the program number 2, I store it in the beginning, the largest size of the program, the one which with the largest size, length, that I store as a program number 1, followed by program number 2 and 3. So if I put the largest size as program number 2 in the beginning, then 1 and 3, so that's 2 first, then 1 and then 3. Then we put the lengths here. The length for 2 is 10, 5 and 3. Let's see how much time it will take us. So program number 2 takes 10 units of time to complete its retrieval, and this takes 10 plus 5, and program number 3 will obviously take me 10 plus 5 plus 3. If we sum it up, it has a total value of 43. If I change the permutation here, I start with the first largest this program, then store the last program immediately followed by this, and then the first program. So this is another possible permutation of this. So that can be 10, in this case 10 plus 3, and in this case 10 plus 3 plus 5, which is a total sum of 41. Okay, let's take one more combination. Let's try and store the smallest program, the program with the least length first. So we start here. Now we can put after this program we can put a program number 1 or program number 2. Let's see both the combinations. If I put program number 1 first and program number 2 first, so that's 3, 1, 2 order. Let's see the lengths of these 3. Now 3 has a length of 3, 1 has a length of 5, and 2 has a length of 10. So what is the retrieval time? For 3 it's 3 plus, for this second program it's 3 plus 5, and for third program it's 3 plus 5 plus 10, which sums up to 29. And if we change the order in this case and put program number 2 first and then program number 1, that means this is the new value. So let's see, what does this equal to? This equals to 3 plus, this is 3 plus 10, and this is 3 plus 10 plus 5, which sums up to 34. Now recall, in the beginning of this lecture what I said is that in the greedy approach that we have been studying for last few lectures is that we select the one wherein we find that immediate benefit. The immediate benefit in this case is that let's store the program with the least length in the beginning of the tape. So if we look at that approach, beginning of the length, first let's store this is the least possible value is 3, followed by 5, and followed by 10. So this is an increasing order. This is a sorted order of lengths. So if I see this particular order with a 3, 5, and 10, that's this one. So 2. Okay, I may have a mistake. It's here. Not the 2. Sorry. It's the last one. This is 3, 1, and 2. 3, 2, and 1. So check this particular combination. 3 has a length of 3. 1 has a length of 5. And 2 has a length of 10. And if we check the value of this combination, this happens to be the least possible value. So what we are doing essentially here is that we are trying our grid in terms of the smallest file size. If we put it in an increasing order of their values of lengths, then we may end up getting a total retrieval value which is the lowest possible value in this case. If we talk of the complexity, if we randomly choose any particular order, then we will have to look at somewhere around n factorial. But if we see the ordered one, where it's increased in terms of its size, then we are talking of essentially any good sorting algorithm, which is a good complexity of n log n. This is how we can optimally store the files on a tape such that the retrieval time is minimized or reduced, such that the minimal time for the retriever. We may optimally store this is one way of storing these programs optimally, such that the minimal retrieval time is lowest possible. With this we finish the greedy method. We'll see in the next lecture. Till then, take care. Bye.